So welcome back. In the previous lecture we started discussing universal gate sets. In particular what we did is we first proved that any unitary gate operation on a register of n qubits can be decomposed into a product of two-level unitaries. Was our first step. The second step that we did last time was that we showed that any two-level unitary can be realized with C0 gates and single-qubit gates, right? And today, what we're going to show is that every single-qubit unitary can be approximated to arbitrary accuracy by using only Hadamard and T-gates. So, and with this, we then finished the proof that every unitary gate operation on a register of n qubits can be approximated to arbitrary precision by only using C0 gates, Hadamard and T-gates. So this is the final goal. And right, so in the previous lecture we already started with chapter 2.3.3, which is now the approximation of single qubit gates by Hadamard and T-gates. And there we introduced the approximation error. So let me briefly recall what the approximation error was. So we said that for V, for a unitary V, which is an approximation of the unitary U, we defined the approximation error as so we said it's E of U and V, and this was a maximization over all normalized states psi in H, and we maximized over the norm of U minus V acting on psi. So this was our definition of the approximation error, and then we proved one specific property which we're going to use today. So it satisfies that if I have E of a product, say U1, U2 to UM, and V1, V2 to VM, then this is smaller or equal than the sum of the approximation errors of the individual terms. Okay, so this was our equation 2.67 the last time. And today we're going to use this. So with this, we now set the stage in order that we can perform the proof. So what we now do is we prove. So we now prove that that any single qubit unitary can be approximated with arbitrary accuracy by Hadamard and T-gates. So first let me give you an outline of the proof, because the proofs involve some calculations, and instead of just calculating it down, I'd like to start with the outline, what I'm going to do in order to prove this. Okay? So the outline. So first we're going to show that that T times HTH is a rotation by an angle theta about an axis n, and we show that HTH times T is also a rotation about the same angle theta, but now about an axis M, okay, with this unit vectors n and m non-parallel, and theta an irrational number of 2 pi. Not of 2 pi, modulo 2 pi. Okay? Since theta is an irrational number modulo 2 pi, we have that a rotation about n by an angle alpha can be approximated by a rotation about n by the angle theta, which is the theta here above, and then we take this to the power L1. So if we perform this rotation L1 times, then we get a rotation by an angle alpha by appropriately choosing L1. The reason is that theta is an irrational number of modulo 2 pi. Similarly, we can get Rm beta approximated by Rm theta to the power of L2. So we can find an L2 such that if I perform L2 times this operation, Rm theta, I get Rm beta. And then the same Rn gamma for an angle gamma. So we can find an L3 such that this applies. And then what we use is that, and this we proved some time ago, that an arbitrary single qubit unitary can be written as a global phase times the rotation about n with the angle alpha, and the rotation by beta around m, and the rotation by gamma about the axis n. Okay, and now you see that except for this arbitrary global phase, if we use this, we can get this unitary simply by concatenations of Hadamard and T-gates. Okay? So this is the outline, and we start now with proving these two equalities here. So first, we recall the definition of the T-gate. And note we use that that we can write e to the I times phi times and then normal vector n sigma as cosinus phi identity plus I sinus phi n sigma. Okay. So we know this relation and we use it together with the definition of the T-gate. So we have T was equal to e to the I pi over 8, and then we had e to the minus I pi over 8, 0, 0, e to the I pi over 8. So this we can write as e to the I pi over 8 times e to the minus I pi over 8 times z, where z is the Pauli z gate. Okay, remember that z was 1, 0, 0, minus 1. Okay. And now we can use this formula here and write this as e to the I pi over 8 times, now we have cosinus of pi over 8 times the identity, and then minus I times sinus pi over 8 times z. This is now our equation number 270. And next, what we use is that the Hadamard can be written as 1 over square root of 2x plus z. And that we can write the Pauli matrices sigma j, sigma k equal to djk identity plus I times the sum over O equals 1, 2, 3. And the Levi-Civita symbol, epsilon, jkl, and sigma l. This is 271. So in particular, this gives x times y equals iz, then y times z equals ix, and z times x equals iy, and y times x equals minus iz, then z times y equals minus ix, and x times z equals minus iy. Okay, so this is simply this relation for all combinations. And the reason that I write it down is that we are now going to use them. So what we want to do now is with this, we calculate, first we calculate HTH. Okay, now let's insert this. For the Hadamard, we use this. Since we have 2 times the Hadamard, this 1 over square root of 2 gets a 1/2. And then we have x plus z. And then we have the T-gate, which is written down here. So we get here a phase e to the I pi over 8. Then cosinus pi over 8 times identity minus I sinus pi over 8 times z. And then again x plus z. Okay, so let's multiply out these factors first. E to the I pi over 8 over 2, then x plus z, and here we have cosinus pi over 8 times x plus cosinus pi over 8 times z. Okay, and then here we have minus I sinus z and x, and zx gives, so it's here, zx gives I times y. So we have plus sinus pi over 8 times y. And here we have z squared, which gives the identity. So we have minus I sinus pi over 8 times the identity. Okay. And now we multiply these two. So it's e to the, I think I use another board because it's going to be long. So this gives us, so first we have x times x, so it's cosinus e to the I pi over 8 half, and then cosinus pi over 8 times the identity. And then we have x times z, which gives minus iy. So we have minus I, and then cosinus pi over 8 y. And then we have x times y gives I z plus I sinus pi over 8 z. And then we have the identity gives minus I sinus pi over 8 times the identity. Okay, and then the other terms are plus z times x gives iy. Yes, so we have plus I cosinus pi over 8y, and then we have x times z gives minus I y cosinus x times z. And then we have, now I did a mistake, right? It's z times x gives iy. This is so correct, and it's z times z is identity. Here's the mistake. So it's plus cosinus times the identity. Okay, and then we have z times y gives minus I, and then sinus pi over 8 x. And we have minus I sinus pi over 8 times z. Now let's see what cancels out. So we have this one canceling with this one, and then we have this one canceling with this one, right? And here I have 2 times cosinus pi over 8 identity, and here's one moment. Okay, this must be wrong. This is x. Okay, and here this is also the same. So it gives e to the I pi over 8, and then we have cosinus pi over 8 identity minus I sinus pi over 8x. And this is equation number 2.73. So and what you see already here is this is nothing else but a rotation by pi over 8 about the x-axis. Okay. Okay. But now what we want to calculate is, so we continue with t times h th. Okay. So we multiply this from the left with t. So we have t times h th. So what was t? T was e to the I pi over 8, and with this e to the I pi over 8 we get a e to the I pi over 4 times, and the t was then cosinus pi over 8 identity minus I sinus pi over 8 times z. And we multiply it with this one here, so we get cosinus pi over 8 identity minus I sinus pi over 8x. Okay, again, let's multiply this out. So we get T HTH is equal to e to the I pi over 4. And then we have cosinus squared pi over 8. Then we have minus I cosinus pi over 8 times sinus pi over 8, and then x. And the next one is minus I sinus pi over 8 cosinus pi over 8 times z. And then 1, 2, 3, one more term. And then we have minus gives plus, minus sinus squared, and then we have zx. Zx is I, gives plus I. No, minus I. Minus zx. Minus I sinus squared pi over 8 times y. It's correct. Plus, minus x. Yeah. Let's rewrite this. So here's the identity. We have cosinus squared in the identity. And then we have minus I times sinus pi over 8. And then we have here a cosinus pi over 8 times x plus sinus pi over 8 times y plus cosinus pi over 8 times z. Well, this we can write as a vector times the vector with our Pauli matrices. Okay. Right, so we wrote this now as a vector times the vector, the Pauli matrices. But this is yet not a normalized vector, so let's normalize this. If we normalize this, we have to divide by the square root of cosinus squared plus sinus squared plus cosinus squared. It gives a square root of 1 plus cosinus squared. Okay, so let's see, this is 2.74 and this is 2.75. So what we see now here is that this combination of Hadamard and T-gates gives us a rotation by some angle. Okay, so this has almost the form of a rotation matrix with a normalized vector n. N is now a normalized vector, right? So and the next as a rotation matrix, right? And So we have to redefine the angle such that we get a nice rotation matrix. So to bring this into the form of the rotation matrix R n theta, which is equal to cosinus of theta half times identity minus I sinus of theta half times n sigma. So this is the form that we want to get. We define, okay, let's look at this. Cosinus of theta half, is this 1/2? Yes, it's correct. So cosinus of theta half must be equal then to the cosinus square of pi over 8. Okay? So we define the angle theta such that cosinus of theta half is equal to the cosinus square of pi over 8. Okay, so now let's take care of this term here. Let's see what's happening here. Then we have here the term sinus of pi over 8 times the square root of 1 plus cosinus squared pi over 8 gives us the square root of 1 plus cosinus squared pi over 8 times the square root of, 1 minus. So instead of sinus, we write now the square root of 1 minus cosinus squared. Okay, this is simply an identity that we know, and then this stays the same. 1 plus cosinus squared pi over 8. Now we use this equation 276. Right, and then we have here the square root of 1 minus cosinus theta half times 1 plus cosinus of theta half, which is simply 1 minus sinus squared cosinus squared of theta half, which is equal to the sinus of theta half. Okay, so what's written here, simply the sinus of theta half. Together, so let's plug this in now here in 274. So we plugging 2.76 and 2.77 in 2.74 gives then that TH is equal to e to the I pi over 4 times the rotation matrix. I'm going to write it out first, okay, times cosinus of theta half identity minus I sinus of theta half times n sigma, which is e to the I pi over 4, and then rotation matrix by the angle theta about the axis n. Okay? And what's important here is that theta is an irrational multiple of 2 pi. So where it's done, so from equation, so from this definition, which is equation 276, one can show that theta is an irrational multiple of 2 pi. So the proof for a proof C, for example, so I just write it down where you can find the proof. It's P.O. Boykin et al. And it's on archive. And you find there on pages 4 and 10. Okay, so this is where you can find that if you define theta in this way, it must be an irrational multiple of 2 pi. I'm not proving it here because of time reasons, but it's important, okay, because we're going to use this in a second. So the next thing that we do is we calculate now HTH times T, okay? So here what we found is that T times HTH gives us a rotation. And now we calculate HTH times T, and we will see that this will also give us a rotation. But this rotation will be now with respect to an axis which is non-parallel to this n-axis. Calculation works similar as before. So we have now HTH times T, which gives, if we plug this in, e to the I pi over 4. So we have 2 times this phase e to the I pi over 8. And then HTH was cosinus pi over 8 times identity minus I sinus pi over 8 times, I think it was x, yes, x, and t was cosinus pi over 8 identity minus I sinus pi over 8 times z. So let's multiply this out. Here we have cosinus squared pi over 8 times the identity. Then we have minus I cosinus pi over 8 sinus pi over 8 times z. And then we have here minus I sinus pi over 8 times cosinus pi over 8 times x. And then here we have plus, minus, and then x and z gives minus plus I sinus pi over 8 squared times y. Okay, now we rewrite this again in a way that we get a rotation matrix. So we have the first term remains, and then minus I sinus pi over 8 times make here, no, go here, this vector. So we have then cosinus pi over 8, this is here, and then we have, for y, we have minus sinus pi over 8, and for z, we have cosinus pi over 8. So this is our vector. Times sigma. Okay. We simply wrote this. Here we always have minus I sinus pi over 8, which we write here in front of these vectors, and then we collected this x, y, and z components into this vector. Okay. And now we again have to normalize this vector. So we normalize this. Let's say this is the vector. We normalize this again by square root of 1 plus cosinus squared pi over 8. And since we divide here by this term, we have to multiply here by this term. Okay, and this vector we now identify as m. So it's equal to I pi over 4 cosinus squared pi over 8 identity minus I sinus pi over 8 1 plus cosinus squared pi over 8. And now we have here the unit vector m times sigma. Okay, with m and now remember, so it's not on the blackboard anymore, but if you remember what the unit vector n was last time, it was kind of the same, but instead of a minus here we had a plus. Okay, and this difference is such that these unit vectors m and n, they are non-parallel, and this is important. So first we rewrite this. So it's actually kind of the very same expression as before. The only difference is the sign here. So we can rewrite this with the same definition of this angle theta. So with theta defined in, okay, it's still there. So with the theta defined in 2.76, we find, similar as before, that HTH times T is equal to e to the I pi over 4, and then a rotation by the angle theta about m. With m and n being non-parallel. Okay. I think we're going to do a break now and then continue in 10 minutes. Okay, let's continue. Before the break, we found that concatenations of Hadamard and T-gates give rotations. So let me briefly recall this. So we found that TH gives e to the I pi over 4 rotation by an angle theta about n, and HTHT gives e to the I pi over 4 rotation by the angle theta about m, with m and n non-parallel, and theta being an irrational multiple of 2 pi. Okay, so this was equation 278, and this was equation 281. Okay, now it is such that since theta is an irrational multiple of 2 pi, if we perform this rotation, so n times, or say we can find a number how often we perform this rotation, such that we find that we get a rotation about an angle alpha. Okay, so let me write this down. Due to the irrationality of theta, so for any angle alpha between 0 and 2 pi, and any accuracy eta or epsilon at epsilon greater than 0, there exists a number L such that L times theta minus alpha, that's the modulus, so such that the modulus of L times theta minus alpha modulo 2 pi is smaller than epsilon. 82. And why? It's since integer multiples of an irrational number fill the unit circle densely. Okay, let's say this again. So for any angle alpha, the angle alpha is the angle that we want to perform a rotation by the angle alpha around some axis. And now given theta, we can always find a natural number, L times sigma, such that the difference to alpha modulo 2 pi is smaller than any accuracy epsilon. So hence we can find an L such that the rotation by theta around n to the power of L is approximately the rotation by the angle alpha around n. So consequently, for the approximation error. This was equation 2.64. We find that for all delta, which are greater 0, there exists a natural number L such that the approximation error of this rotation by theta, so if I rotate L times by theta, compared to the rotation by alpha, is smaller than delta. And what this says is exactly that we can approximate the rotation by an arbitrary accuracy, right? So we can always find a whole number such that if we perform this rotation by theta L times, then it is very close to this rotation by alpha. And it's actually as close as we want it to be. So finally, recall that any single qubit unitary can up to an unimportant global phase be written as u equal to the rotation by angle alpha about n, rotation by an angle beta around m, and rotation by gamma around n. So this is what we've seen some time ago. Let me stress again, up to an unimportant global phase. Then the results, which is 278, 281, and 2.84, which is this one here, didn't give it a number, 2.84. Therefore, imply that they imply that for all delta greater or equal 0, there exists L1, L2, and L3, which are natural numbers, such that space here, such that the approximation error E of R n theta to the power of L1, R m theta to the power of L2, and R n theta to the power of L3. So whether this approximates R n alpha, R n beta, R n gamma. So now what we use is equation 2. So by equation 2.67, which I recalled today at the beginning, that this is smaller or equal to E, so the approximation error of R n theta to the power of L1 and R n alpha, plus the approximation error of R m theta to the power of L2 and R and beta plus space E of R and theta to the power of L3 and R and gamma. And well, by our results, now by 284, we find that this is smaller or equal to 3 delta. Okay. And what this shows is now that any single qubit unitary can be approximated to arbitrary precision by Hadamard and T-gates. The reason is that these rotations are simply concatenations of Hadamard and T-gates, and what this now tells us that we can find combinations of Hadamard and T-gates such that the approximation error to our single qubit unitary is smaller or equal to 3 delta, and this holds for for all delta greater than 0. And it's exactly what we wanted to show. Okay, so this kind of finishes the proof. And before we come to the next section, I'd like to state some remarks. The first thing is about the scaling. Okay, so how does it actually scale? What we found so far is only that there is such a decomposition, or there is such a way how we can perform any single qubit unitary by concatenations of Hadamard and T-gates. But so far we didn't state how many of them do we actually need to get some precision, right? So this is actually specified by the so-called Solovay-Kitaev theorem. Okay, this is a theorem that I'm not going to go into detail further. You can look this up in the book by Nielsen and Huang, for example. There's Appendix 3. There, I think they proved this Solovay-Kitaev theorem. And let me just write this down. So, scaling resources. By the Solovay-Kitaev theorem. An arbitrary single qubit gate U can be approximated to an accuracy epsilon. So this epsilon is here this epsilon, an arbitrary accuracy epsilon using O log 2 of 1 over epsilon to the power of c gates from the discrete set so the discrete set is Hadamard or T-gates, and this constant c is approximately 2. Okay, so it tells us the better the accuracy we want to have, meaning the smaller epsilon, the more H and T gates we need. That's what it tells us, and the scaling is pretty okay. And then let me also recall that in section 2.3.2 we found that O n squared 4 to the power of n single qubit and C not gates are required to implement an arbitrary n-qubit unitary. So we can conclude that by combining these two scaling behaviors, that if we want to perform an arbitrary n-qubit unitary, we do need an exponential number of gates from our finite gate set. Right, so exponential in the number of qubits. So altogether, okay, so just saying again that if you put this together, we do need in general an exponential number of gates from our discrete gate set in order to perform an arbitrary n-qubit gate. Okay, and this, as I already mentioned several times in this lecture, it is now such that this the way how we decomposed it, so this way how we decomposed this n-qubit unitary is often, very often, not fortunate in order to come up with a circuit such that we can implement a unitary efficiently. Okay, and this is the reason. The scaling behavior is this reason. But of course, the scheme that we used here is not the only way how you can implement unitaries. This was just a general scheme. Okay? We ask, can we implement an arbitrary unitary? So if you have a particular unitary in mind, it's possible that you can come up with a way such that you can find a circuit which does not scale exponentially in n, but scales, for example, polynomially. And indeed, if we want to, or if we study quantum algorithms, we do need such a circuit representation which does not scale exponentially in n. Okay? And there's one particular unitary transformation, which is the so-called quantum Fourier transformation, for which we know a circuit which scales polynomially in n. In particular, it scales as n squared. Okay? And this quantum Fourier transformation is important for many algorithms. So the most famous one is Shor algorithm. So quantum Fourier transform is really at the heart of Shor's algorithm. And the reason is that with the quantum Fourier transformation, you can do what we call quantum phase estimation. Right? This is quantum phase estimation. We're going to discuss an algorithm for quantum phase estimation at some time. And with quantum phase estimation, you can then perform this in order to do Shor's algorithm. Okay? So we are not in this lecture. We're not going to discuss Shor's algorithm as it is in detail, right? But what we discuss is phase estimation. And once you understood phase estimation, you have all the tools from this quantum mechanics point of view that you need in order to understand Shor's algorithm. The only more ingredient that you need for Shor's algorithm is then some more mathematics, right? Some number theory that you need. But we're not going to do this because this would take us a bit too much time. But if you'd like to understand Shor's algorithm, I know that many students would like to understand this, then I recommend just open the textbooks and continue reading, because with what we do in the lecture, you're almost there to understand this. In particular, what we discuss is the quantum part of this algorithm. Okay, so this actually now brings me to our next chapter, which is the quantum Fourier transformation. So the quantum Fourier transformation is now the last ingredient that we need in order to then study some quantum algorithms. Okay, so I think the quantum Fourier transform will take us the rest for today, and then possibly a bit next time on Monday, and then we are set to study quantum algorithms. 2.4, this is our section 2.4. So, and actually I already motivated why we want to study this quantum Fourier transform in a bit more detail. And actually what our aim is now, first we define this quantum Fourier transform. We're going to see some properties, some basic properties, and then our aim is to find a circuit such that we can implement this using only O n squared single qubit and C0 gates. Right? And this, in order to do so, we will have to do some steps. Okay, but let's first define the quantum Fourier transformation. It's definition 2.4. So we define it, the quantum Fourier transformation, as a linear operator acting on some orthogonal or ON basis. Okay, suppose this state 0 to n minus 1 is an orthonormal basis. Then we define this quantum Fourier transformation as a linear operator which acts on the states as follows. So we have f acting on j is equal to 1 over square root of n, and then the sum j equals 1 or 0 to k equals 0 to n minus 1, then e to the I 2 pi j k divided by n, and then basis state k. So this is how it's defined. So the first remark is to see how the Fourier transform looks in the outer product representation. Okay, so using that k f j. So if we multiply here from the left, let's say, with our bra k, then we get 1 over square root of n, and then e to the I 2 pi j k over n. Okay, and suppose that this, we do this using this, we can write the quantum Fourier transform in the outer product representation. As f equal to sum over jk equals 0 to n minus 1, and then we have 1 over square root of n, e to the I 2 pi jk over n, and then k j. Okay, the second remark is that quantum Fourier transform is unitary. Okay, so f is unitary. This means that f dagger f is equal to f dagger is equal to the identity. So where the adjoint of f acting on j is equal to sum over k 0 to n minus 1, then we have 1 over square root n, now e to the minus I 2 pi jk over n. Okay. And I think you're going to prove this as an exercise. And then the third remark is simply notation. So since f is unitary, it represents a basis transformation. And we denote basis states by Pj is equal to the Fourier transform on J. So I think by the definition, you already see that it is a discrete version of what you know from the Fourier transformation. Okay, and this notation here also comes by this relation to the Fourier transformation of a continuous space. Right now, here we're in a discrete space. So it's a discretized version of this Fourier transformation in continuous space. And in the following, now here how we defined it is we didn't specify capital N, but if we of course take small n qubits, then capital N is 2 to the power of n, right? So because capital N is the dimension of our state space. So in the following we consider n qubits such that capital N is equal to 2 to the power of n. And the basis states are 0 to 2 to the power of n minus 1. Okay, so this is the definition of the quantum Fourier transformation, and our next aim is to find a circuit which is efficient. So which we want to find a circuit diagram which can be implemented efficiently by only using a small number of C0 and single qubit gates. And in order to do so, I now have to introduce some notation, namely I'd like to discuss a bit more the binary representation, such that in the end we can introduce the so-called binary fraction. Okay, simply a notation. You will see it in a second. So this notation allows us then later on to rewrite the quantum Fourier transformation such that we can immediately see how to perform this transformation with a circuit diagram. Okay, so we want to rewrite this now, and from this new representation, we can then figure out a circuit. In order to rewrite this, I first like to discuss this binary representation. So first, recall that the basis state labels J, which run from 0 to 2 to the power of n minus 1, which means Okay, what is it? You can write j as j n minus 1, 2 to the power of n minus 1 plus j n minus 2, 2 to the power of n minus 2, and so on, until we got j0, 2 to the power of 0, which is the sum over L equals 0 to n minus 1 of jl 2 to the power of L. This is 2.90. With, okay, this coefficients jl is either 0 or 1. Basis state labels. They can be expressed in binary representation by j is equal to these coefficients jn minus 1, jn minus 2 to j0. Okay, this is nothing new. We've seen this already, which is simply a transformation, or the different notations that we use. So let me do an example. I mean, I guess all of you either you see it already, or when I do the example, you see that this is nothing else that we've done all the time. So for example, suppose we have, so for n equals 3 qubits, we have that 6 is equal to 1 times 2 to the power of 2 plus 1 times 2 to the power of 1 plus 0 times 2 to the power of 0. So it's 4 plus 2. Or in binary representation, this reads 0, 1, 1, 0. Okay. So it's there we simply write these coefficients here. Now it's getting a bit more interesting. So now consider what happens if we have j divided by 2 to the power of L. Okay. Now we can insert equation 2.90. So we get a sum over L equals 0 to n minus 1 jl, and then we have 2 to the power of L minus, okay, it's not a good index. You have to use Q here. Q, and then we have 2 to the power of Q minus L, let's say 2 to the power of q divided 2 to the power of L. Okay. And now let's rewrite this. First, we take q from 0 to L minus 1. Then we have jq. And we have 1 over 2 to the power of L minus q. Okay. The reason that we do this is that here we have that q is smaller than L. Okay. So since q is smaller than L, this fraction here is smaller than 1. Okay. And then the other term, the remaining summands, we have q equal to L from L to n minus 1, jq, and then we have 2 to the power of q minus L. Okay, and here we have q is greater or equal to L. Okay, so we simply split the sum into summands which are smaller than 1 and summands which are greater or equal to 1. So now let's rewrite this. So we have j naught, which is the first term, divided by 2 to the power of L, plus j1 divided by 2 to the power of L minus 1, and so on, until we are at jl minus 1 divided by 2 to the power, by 2 to the power of 1, plus then we have jl 2 to the power of 2, plus jl plus 1, 2 to the power of 1, and so on, to jn minus 1, 2 to the power of n minus 1 minus L. Okay, so this expression we know. If you compare with 290, okay, this expression we know. We can now write this. So first we note that this is a natural number, and we can write this in a way. So if we write this in this way, we have jn minus 1, jn minus 2, to jl, jl minus 1, jl minus 2, to, no, it's wrong, to L. Okay, so this is now the binary representation of this number. If you compare this with equation 2.90. And now for this first term, we introduce now a notation which we call the binary fraction. So we write this as very, very similar as here. We write this as O.jl minus 1, jl minus 2 to j naught. Yes. So this is how we write this term. And this we call the binary fraction. And this is O point and then this number. And if you put them together, we can write this as jn minus 1, jn minus 2 to jl, and then point jl minus 1, jl minus 2 to j naught. So where we introduced the binary fraction point JL minus 1, J minus 2. Okay, this is simply a notation. And this notation makes actually pretty much sense because it tells us that the first element here after the dot is you multiply it by 1/2, and this is multiplied by 1/4, 1/8, and so on, right? So here, for example, here go back to this notation. Here we have JL to the power of 2 to 0, as times 2 to the power of 0, then times 2 to the power of 1, times 2 to the power of 2, and so on. And on the right hand side of the dot, we have this times 2 to the power of -1, to the power of -3, to the power of -4, and so on. So this notation with this dot here makes really very much sense. It's simply a continuation of this binary representation. And that's where the name fraction comes from, the fact that those elements on the right hand side are always multiplied by this fraction, which is 1 to 2 to the power of something. And this notation allows us to rewrite the quantum Fourier transformation. And I think I'm gonna do this next time, because we're not finishing this in 5 minutes. Possibly we can. Should we continue 5 minutes, or should we finish? Let's do it next time. Okay, I think it's enough for today. Has been a lot. So next time we're gonna use this binary fraction and we rewrite the quantum Fourier transformation. And then with this new form, we're gonna find an efficient circuit. Okay, see you next time.